Next Monday, I mean, if you don't count today's Monday as a Monday, then yes.
Okay, so like the coming Monday.
Yeah. So 15th April, right? That's the starting date.
Yeah, I guess.
All right. So today, as we discussed last time, first we are going to do a paper two all by yourselves today. And then I'll also give you one as homework. And because we'll have some time before Monday as well. So we'll have class on Sunday or Saturday. I'll let you know.
Okay.
But then as well, we can do another paper then. All right.
All right.
Let me just first see where this went. Mm. So today we are starting with some of the older papers. So today we are doing summer 21, paper 21, because as I said, we are going to be doing the more recent ones in the sessions.
Okay.
All right. There's this static on your side.
Um, I don't know what to do.
Do you have your phone near your computer or something?
I had my phone near my microphone, but
Yeah, just remove it from there. I think that's the
it's
problem.
gone. Is it better?
Yeah, it's gone now.
Oh, I didn't know the
Yeah,
phone did that.
you're probably too young to remember the times that when you put it near the TV, the screen just goes away. The older
Really?
TVs. Yeah, it's because of electromagnetic interference.
Wow.
All right, so summer 21, paper 21 is what we're starting with. Now, you know that for all paper twos, you have 1 hour, 15 minutes. And we also talked about this last time out.
Yeah.
Even though we have 15 minutes extra, we'll be restricting ourselves and trying to do this
In 1 hour.
just a time of 60 minutes. So
So you have
let's,
time to fill out or recheck your work.
yeah. So let's start this. Get started. So formula sheet, formula. All right. So in this paper, you can also obviously give your input, but just to let you know how my mind works when solving a paper, I'll just be thinking out loud. And then you can try to understand that as much as you can. So for example, the first part, define density. So this is pretty easy. What's it going to be?
Mass per unit volume.
Yeah, pretty easy. So
Yeah.
mass per unit volume. All right, next one. So 1.1 shows a solid pyramid with a square base. The mass of the pyramid is given by this equation 1 by 3 rho hx squared. Rho is density, h is height, x is the length of each side of the base. Measurements are taken as shown, and then you have all of these quantities, and then you have the measurements given as shown. So the first part asks, calculate the absolute uncertainty in the length x. Now this is pretty easy to do because if I look at the column for x, then I have the measurement and I also have the percentage uncertainty, right? So
Yeah.
for the absolute uncertainty, I would just need to take that percentage from this quantity. So all I would do is take 5% of 4 centimeters, right?
Yeah.
So if you take 5% of 4, this will turn out to be 0.2 centimeters. Again, really a free mark here. Now on to the next part. The density rho is calculated from the measurements in table 1.1. Now this is always, if not always, if it's going to be the case most of the time, that some equation will be given to you, but then you will have to probably work around with this equation. Now what I mean here is this, that in this equation, m is the subject, right? But
Yeah.
I need to calculate density, and more specifically, not even the density, I just need to calculate the percentage uncertainty in the calculated value of rho. So if I make rho the subject here, then you can see this is going to be 3m over hx squared, right?
Yeah.
Now I see that there are three variables here. There's the m, there's the h, there's the x, and they're all either getting multiplied or divided. Now my mind clicks to the rule that if variables are being multiplied or divided, their percentage uncertainties would be added, right?
Yeah.
But because this one is also raised to a power, this uncertainty will be multiplied by the power. So then it's really easy. I'm just going to write first here that what the expression will look like. So the percentage uncertainty in M in rho is going to be the percentage uncertainty in M plus the percentage uncertainty in H plus twice the percentage uncertainty in X. Make sense?
Yeah.
Plus twice the percentage uncertainty in X. So once I've written this, then I'll go to the table. And in this one, I don't even need to calculate anything, right? You just look at this here. I'm already given the percentage uncertainties. So for M, it's 2. For H, it's 4. And for X, it's 5. So twice of 5. So 2 times 5 is 10 plus 6 makes it 16%. All right.
Yeah.
Are you copying this as we go along?
Should I? One
Yeah, you
second.
should.
All right. Can I just use the bathroom really quickly?
Sure.
You can maybe pause the timer or something.
Yeah, I'll do that.
All right. All right.
All right. So yeah, just go ahead and copy the stuff quickly. The first part was just the mass per unit volume part.
Yeah.
Let's do this quickly so that we can go on. In this one.
All right.
All right. So the next part, then part C, says the square base of the pyramid in B rests on the horizontal surface of a bench. Use data from 1.1 to calculate the average pressure of the pyramid on the surface of the bench. Uncertainty is not required. So it says pressure. So if I go back here and if I also look at this diagram, so I can see that this is resting on a square base, right? So
Yeah.
I know this dimension. So I can very easily find out the area. It's just going to be x squared. But if I want to give my answer in pascals, then I would need to convert this. All right.
Yeah.
So it would just be x squared. So 0.04 squared. That's going to be the area. And I have the mass. So by multiplying by small g and converting this to kg, I would also have the force, right? Or the weight.
Yeah.
And then I can just use P equals F over A. So P equals F over A, right? So a seemingly very easy question is giving you 3 marks away. So you just need to take care of the conversions. This was 19.5 grams. So 19.5 into 10 to the negative 3, right? This is into kg now. Then multiplying by small g makes this force. And area is going to be 0.04 squared. This is pretty straightforward, right?
Yeah. Let me
So
just.
this turns out to be
Oh, okay.
120. Yeah, just confirm. Go ahead and confirm.
19.5 times 10 to the power negative 3 times 9.81 over 0.04 square. You get 119.5, so 120.
Yeah. All right. Question 2. A person uses a trolley to move suitcases at an airport. The total mass of trolley and suitcases is this much. The person pushes the trolley and suitcases along a horizontal surface with a constant speed. In questions related to forces, as well as questions related to work energy power, this should be a phrase that you should really take care of. Because constant speed means that the resultant force on this is 0, right? Why does it mean this? Is because if the speed is constant, then this implies that the acceleration is 0. And by Newton's second law, it also implies that the resultant force is 0. All right.
Yeah.
So constant speed of this much and then releases the trolley. The released trolley moves in a straight line and comes to rest. Assume that the constant total resistor force of 18 Newton opposes the motion of the trolley and the suitcases. Calculate the power required to overcome the total resistive force when they move with a constant speed of 1.4 meter per second. All right. So if we want to find the power, because I see velocity here, the formula that comes to mind is this one. All right.
Yeah,
Now you can see that this moves at constant speed. Yes. So if
yeah,
this moves at constant speed, this means that if this is the trolley and the suitcases, if this is moving in this direction, and if I know that the resistive force is 18 Newton, then for this to move at constant speed, the forward force must also be 18. Does this make sense?
yeah,
So the force is 18. Always remember that in this formula, we talked about this as well when we were discussing work energy power. It's not the resultant force that comes here, right? In some
yeah,
cases, we might be dealing with a vehicle, and in that, it would be the driving force. So it would say the power developed by the car. In this case, it says the power required. So what power does this force exert, right? So it's going to be 18 times 1.4. So this is going to be 25 watts. All right.
yeah.
All right. Now the second part, time taken for the trolley to come to rest after it is released. Now, how do we do this one? So in this, we see that there was a force acting of 18 Newton, right? And when he releases the trolley, there's no more push, right? So there's no more this force. Now there's just this 18 Newton, which is going to decelerate the trolley. Do you understand this?
Yeah,
So then I can first find out acceleration, right? So the force is negative 18 because this is slowing the object down. Or you can also say because it is to the left, that's why it's negative. Mass was given as 72 and this is A. So I can find out A as minus 0.25 meter per second square. Now, what do you think happens next? Because now we have acceleration and we need to find the time. Hmm?
yeah,
So we have acceleration.
yeah.
What else do we have? It comes to rest, right?
So we have
So do we know its
final
final
volume.
velocity? Yeah.
Yeah,
What is it?
final velocity, I mean, 0.
And what's the initial velocity here?
Constant speed 1.4.
Yes, so that's 1.4. And I have A as negative 0.25.
V
And I
square
want
equals U square plus half AT.
no,
S equals U
because in
square
this
plus half
one you
AT.
need time, right? So you have
Yeah,
VUA and you need T. So here you use V equals U plus
U
AT,
plus AT, right?
right? So
Yep,
V minus U over A. So 0 minus 1.4 over minus 0.25. So this turns out to be 5.6 seconds.
yep.
All right.
1 second.
Does this make sense?
Yeah.
All right.
Where was the 18 from in the first part? Just want to double check.
This is because we know resultant
This is the
force is
force of
MA.
18.
If
Mm.
it is released, so now there's no more of the person who's pushing and who's applying this force, right? So the
Yeah,
only force which then exists is this one, which is going to slow down the trolley because it's going forward, but the resultant force is acting backwards.
okay.
Hence the negative.
Yeah,
Already done.
just like 10 more seconds. Okay,
Then it says at another place in the airport, the trolley and suitcases are on a slope. The person releases the trolley from rest at point X, right? So this is release from rest. The trolley moves down the slope in a straight line towards point Y, and the distance is given. All right.
Yeah.
The component F of the weight of the trolley and suitcases that acts along the slope is 54, right? So this is the component which is going to push it down. And the resistive force is still the same. This is 18. Now, even before going into this question, will this trolley now move at constant speed or will it move differently?
Move differently. Increase in
How?
speed.
Excellent. It's now going to accelerate because as you can see, there's going to be a resultant force. Yes?
Yeah.
54 forwards, 18 backwards gives us, I guess, 36 forwards. So there is some resultant force. All right.
Yeah.
So it says calculate the speed of trolley at point Y. Now, how do we do this? The speed of the trolley at point Y. So yeah, I guess we can still find out acceleration. Yes, by Newton's second law. The mass is still the same. We now have distance. So we would have distance, acceleration, and we have initial velocity, right?
Yeah.
Then we can use an equation of motion. So first we would do F equals ma. So resultant force in this case would be 54 minus 18 equals 72A. All right.
Yeah.
So A from here would turn out to be 0.5. Now this time it's positive meter per second square. Right?
Yeah.
So this is 0.5 meter per second square. Does it make sense why it was negative before and why it's positive now?
Yeah.
All right. So now we have A. We also have U as 0. We want to find V. We also know the distance, 9.5. And we have A as well. Right? So what
Yeah.
equation of motion do we use this time?
V squared equals U squared plus 2AS.
Exactly. So there is no U square term here because it's 0. So it's just root of 2AS, right? So 2, 9.5, and 0.5. So this turns out to be 3.1 meters per second. Okay.
1 second. 9.5. And the final answer is 3.1 meters per second. Okay.
All right. Part 2. Work done by F for the movement of the trolley from X to Y. So what force was F? This 54 is F, right? So
Yeah.
work done would be pretty simple. What's the formula for work done?
Work done equals force times distance.
Yes. So I have force 54 and I have distance 9.5. So this is just 54 times 9.5. So this turns out to be 510 joules. Part 3. The trolley is released at point X at time t equals to 0. On 2.2, sketch a graph to show the variation with time t of the work done by F for the movement of the trolley from X to Y. All right.
Yeah.
Numerical values of the work done and t are not required. Now, whenever you have to make a graph, always try to find a relationship and then plot the graph according to this. Now, what we were just looking at, we know work done is force times distance, right?
Yeah.
Now, in this case, the distance is going to obviously increase as it moves down the slope. And if I think about distance here, I know that distance is going to be, I can write it as, if I just use an equation of motion. So I know it's going to be ut plus half at square, right? Why am I doing this? Is because I need a relationship between work and time. I see work here, I see distance here, but I don't see any time. All right. So I'm trying
Yeah.
to figure out a relationship between work and time. Now I know this thing is going to be 0 because initial speed is 0. So this is just F times half a t squared. Now, if you get rid of all the rubbish, you can see work is just proportional to t squared. Yes.
Yep.
So this really is pretty much like y equals to x squared. How does this graph look like?
Y equals to x squared.
Hmm.
Is it gonna be like a U shape?
Yes, very good. It's going to be like this. All right.
Mm-hmm.
All right. Part C. Did you get the reasoning for this graph? Does this make sense?
Yeah.
All right. Part C. Angle of the slope in B is constant. The frictional forces acting on the wheels of the moving trolley are also constant. Explain why in practice it is incorrect to assume that the total resistive force opposing the motion of the trolley and the suitcases is constant as the trolley moves between X and Y. It says that in this entire motion that we were considering, you saw that we took it as, we took the frictional force as 18 Newton throughout, right?
Yeah.
Now it says, why in practice would it be incorrect to assume that that force is constant? What do you think?
I don't know.
As the trolley was moving from X to Y, what was happening to its speed?
Increasing.
So do we know of a resistive force that increases with speed?
No
Think again.
friction.
Be more precise.
What?
Air resistance,
Uh,
right? So since the speed is increasing here, we know that the air resistance would also increase with speed. So this is why it's incorrect to say that it would be constant. All right.
yeah.
So don't think about it generally, think about it according to this scenario. It said as the trolley moves between X and Y. All right. Question number 3. A pendulum consists of a solid sphere suspended by a string from a fixed point P, as shown in 3.1. Sphere swings from side to side. At one instant, the sphere is at its lowest position X, where it has kinetic energy this much and momentum this much in a horizontal direction. A short time later, the sphere is at position Y, where it is momentarily stationary at a max vertical height above position X. The string has a fixed length and negligible weight. Air resistance is also negligible. On 3.1, draw a solid line to represent the displacement of the center of the sphere at position Y from position X. So this is X, this is Y. It says mark the displacement of the center of the sphere. So would it be a line like this?
Displacement? No, it'd be a straight line.
Excellent. So this is just going to be a straight line. Remember that it's going to be from center to center because that's what the question says.
Yeah.
All right. Part B. Show that the mass of the sphere is this much. Now, if we look at this, for the initial part, I can see that at X, I have the kinetic energy and I have momentum, right?
Yeah.
So if I think about kinetic energy, that's half mv squared. And momentum is what?
Momentum is 0.72. Yeah, MV.
Yeah. So now if I think about this, I have 0.86 as the kinetic energy. I have half as, I have half mv squared, right? And
Yeah.
similarly for the momentum, I would say 0.72 equals mv. Yes.
Yeah.
Now from this equation, I can see that because I want to find out m, I should make v the subject here. Yes, because I want the v to go away, right?
Yeah.
If I want the v to go away, then I should make v the subject here. So v would be 0.72 over
Over M.
M. So 0.86 equals half M. 0.72 over M, but this is squared. All right.
Yeah,
So when I work with this, this is going to be 2 times 0.86. And this M and the M square would cancel out so that I would have 0.72 squared over M here. All right.
okay.
Does this make sense, the algebra?
Yeah,
Then you just make M the subject. So when you make M the subject, this will turn out to be 0.3 kg to 2SF. Can we go forward?
yeah.
In the next part, it says calculate height h. Now, how do you think we would calculate this height h?
Pythagoras theorem.
No, it says the height h. You don't know the displacement. In the
Uh,
first part, you just made a line. What was this
uh,
question on? It's on energies, right?
yeah,
Does it have any potential energy here?
yeah.
No, because if this is the lowest point, then it is at the lowest point, right? So it has no potential energy here. It just has kinetic energy. And at this point, what sole type of energy does it have?
0.86 joules potential energy, gravitational potential energy.
Yes. Now it's just GP, right? So
Yeah.
0.86 equals mgh, and then you can find out h.
Oh,
So 0.86 equals, now whatever this value was, because I'm looking at this from a solution. So actually, whatever value you got from a calculator, you should use. So 0.30 times 9.81 times h. All right.
yeah.
And when you make this the subject, you should get this.
0.29. Yeah.
All right. Part D. Distance between point P and the center is 0.93 meters. All right. So let's go back up to the diagram for this. P and the center. P and the center. Yeah. So this distance, which is marked, is 0.93. And they want us to calculate this angle. How can we do this? So we just found out h, right?
Yeah.
So by subtracting these, I can get this height. And then what else do I know? If this length is 0.93, isn't this just the length of this string?
Yeah.
What else did the question say?
String has a fixed length and negligible weight.
So at this point, what would this length be?
0.93 or whatever
Yes.
it is.
So
Yeah,
then this just
0.93.
becomes a right angle triangle like this.
Yeah.
This length would be that 0.93 minus what we just found out, 0.29, right? So this is going to be 0.93 minus 0.29. What does this turn out to be? 0.64. This is 0.93. And now you just need to find out this. So what trigonometric ratio do we use here?
We have hypotenuse and adjacent. So a sine.
No, this is cos. Adjacent over hypotenuse is cos. Sine is
Adjacent,
opposite over.
right.
So cos inverse 0.64 over 0.93. Cos inverse 0.64 over 0.93. So 2SF 47 degrees.
How many questions are left?
I guess a lot.
Yeah.
For the sphere at position Y, calculate the moment of its weight about point P. Again, we need to go back to the diagram for this. For the sphere at Y. So now we need to find the moment of this weight. Let's mark the weight about point P. All right.
Yeah.
Now, what are we thinking? How would we find the moment? So this is the pivot. This is the distance. But you know the formula for moment is force times perpendicular distance, right? Right now,
Yeah.
this distance and this force are not perpendicular. So what's on your mind? What should we do next? We just found out this angle, right? This should give
Yeah.
you some hint.
Um. Which one? What is it? I don't know.
So if we resolve this force into this and this, yes.
Yeah.
Now this one, as you can see, this force is now perpendicular to this distance. No?
Yeah.
Now because this one was theta, then by angles, this one is also going to be theta, right?
Yeah.
So this component is going to be W sine theta, but is this the one I want?
No, you want the other
Then
one.
it's the other one, right? So then
Yeah.
it's W cos theta times this thing, right?
Yeah.
Actually, just a sec. Sorry, this one is going to be cos. I'm sorry. This one is with the angle, right? So this is going to be cos. So I need the other one. I need this one, which is going to be sine. All right.
Yeah.
So this is the force. What's this distance going to be? We just did this.
0.98, 0.92.
Yes. So W sine theta times 0.93. For W, I found the mass. So W equals mg. So 0.3 multiplying by g multiplying by sine 47. All of this is the force part. And then I just multiply by the distance, 0.93. All right, moment equals force times perpendicular distance. All of this is the force part, and this is the distance part. So we should get 2.0 Newton meter. Part F. State and explain whether the sphere is in equilibrium when it is stationary at position Y. So is the sphere in equilibrium?
When it's stationary at position Y, yeah. No.
What do you think we just found out in part E?
Yeah, no, there's moments. It's not.
Yeah, resultant moment is not zero. So you can say this is not an equilibrium.
Yeah.
So resultant moment. So not in equilibrium. All right.
Yeah.
Seems so easy right now.
Yeah, because you're doing it.
Yeah. But again, this is the exercise. Once you get comfortable with me doing it, hopefully when you do it on your own, you'll also slowly but surely get comfortable with it. For a
Inshallah.
progressive wave, inshallah, state what is meant by wavelength. So for wavelength, when we were studying waves, remember I told you like one or two ways to define this. Do you remember anyone?
But state what is meant by a wavelength.
Mhm.
Speed per frequency.
No, that's not the definition. Yes, you can change the equation to make it the subject, but that's not the definition of it.
I don't remember.
All right. So there are two ways really to define this. First, you can say this is the distance moved by the wave in one time period, right? Distance moved by the wave front in one time period. Or you can also say in terms of this idea that you know that if I make a wave like this, then this would be the wavelength, right?
Yeah,
So you can also say the distance between two adjacent crests or two adjacent wave fronts. All right.
yeah,
So distance between two adjacent wavefronts. All right, how about part B? Light wave from a laser. So light wave from a laser has a wavelength of this much. We need to find the period. So we have lambda, right? So in your mind, you must be thinking of this equation. Yes.
yeah,
Once I can find out F, then I can also find out the time period, which is just going to be the reciprocal. But the problem is, what is V here? What is V here?
speed,
Speed of what?
speed of the wave,
And what is the wave? Look at what
light
I'm
wave,
circling here. Yeah, so what's the speed of light?
speed of light, 3 times 10 to the power of 8.
Yeah, so what's the problem then? 460 into 10 to the negative 9. So then you get the frequency, and then you just do 1 over that
Yeah,
to get the time period. Should be turning out to be 1.5 into 10 to the negative 15 seconds. Light from the laser is incident normally on a diffraction grating. Describe the diffraction of the light waves at the grating. So, how would we describe the diffraction? What does diffraction really mean? Hmm? If I just ask you to tell me what is diffraction,
diffraction,
it's the spreading of a wave,
the
right?
spreading or the way a
But
wave
when does
diffuses
that
past
spreading happen?
when there's an obstacle in the way.
Uh, if there's an obstacle, then how would it really
Like the
spread?
grating, I guess, through the hole,
Yeah. So
through
what
a
does the grating
small,
contain? It contains small holes, right?
yeah,
Contains slits. So you just say that waves pass through the through the slits, and they spread.
yeah,
All right.
yeah,
Part D. A diffraction grating is used with different wavelengths of visible light. Angle theta of the fourth order maxima from the zero order is measured for each wavelength. Variation with lambda of sine theta is shown. So this is a question on graphs. And again, notice here that lambda is given in nanometers. All right. This is
yeah,
something you will need to take care of when working with the equation. It says the gradient of the graph is G. Determine an expression in terms of G for the distance between the centers of two adjacent slits in the diffraction grating. Now, what's the diffraction grating equation?
what's the d sine theta equals m lambda?
Good job. And now we need to somehow include the gradient, right? We need to work our gradient into this expression. Now on the y-axis, we have sine theta. On x-axis, we have lambda, right? You know gradient is y over x, right? Change in y over change in x. So if I have sine theta over lambda, that would just become g, no?
Yeah,
And additionally, we also know this is the fourth order, right? So this is really d sine theta equals 4 lambda. So if I make this sine theta over lambda, and if I make this, so this would basically be my gradient, right? And this would become 4 over d. So this is my expression. So since g is 4 over d, then D would also be 4 over G. Does this make sense?
Yeah.
All right. Now for part 2, you need to think about this. On 4.1, sketch a graph to show the results that would be obtained for the second order maxima. Now this was for the fourth order maxima, right? So you had 4 here. For the second order maxima, what would the gradient expression look like? Hmm?
For the second order maxima, 4 over G.
No, look, the gradient was 4 over D. Look at this.
Yeah.
G was 4 over D, right? If it's
Yeah.
now talking about the second order maxima, how would this equation change? G would now be equal to what?
8 over D.
Hmm?
8 over D.
Why would it be 8?
Because it's multiplied by 2. Or
No,
is it divided? It's divided.
because how did this 4 even come about? Is when you substituted 4 for the n, right?
Yeah.
And now what you would do? You
So
would
it's
just
2
substitute
over
instead of
D.
n, you would substitute 2. So it's 2 over D,
Okay.
right?
Yeah.
All right. So now if we think about this, so you can see this, which gradient is larger? First of all, just tell me this.
Which gradient is larger?
Hmm.
The 4 over G.
4 over D, right?
Yeah.
So I just need to make a line which is now half as steep. Does this make sense?
Yeah.
So if I go to this graph here, and I just need to make it for the visible light, I guess. Yeah, this is just for visible light. So this goes from here till, how far up does this go? So if I look from here, this goes like this box, and then
Need to
1,
go
2,
up to
3,
that's it.
4. Right, so this should now not go as high up. Should go like
Yeah.
this.
Yeah.
All right, but it's a bit difficult to do because I'm doing this on the iPad.
Yeah.
So this many boxes and then roughly half of that.
Okay.
Hmm. Yeah. No, just a sec, just a sec, just a sec. No. The problem is this. This point should not be the same. Now, because this is half as steep, so how this should go is, look at this. You know, if I take this back, this would pass through the origin, right? Because there was no y-intercept as was evident in that equation. So now if I make this graph is now not going to start from here. Because this is the gradient, right? The gradient is included in this. Now, because this is half as steep, so how many boxes high was this? So this was 5 and then this was 6. So I'm looking at 3 approximately. So the graph starts from here. And previously it was going up to 10 boxes, right? So now it should go as half as high. So now it should
5
just be 5 boxes, right? Sorry for the confusion. This is how it's going to be.
Yeah.
All right, 5 part A. Have a crack. Kirchhoff's second law. The voltage law is the second law.
voltage. This is where with the voltage across. It's the voltage divider law.
No, it's not Kirchhoff's second law. Don't forget this stuff. We worked so hard on this.
1 second. The sum of EMFs equals sum of potential difference.
What else do we need to say?
in a closed circuit.
Yes, good job. Part B, a battery has EMF this much, internal resistance this much. So whenever I see a question of internal resistance in my mind, I've already started thinking about this equation. You remember this equation?
Yeah,
This is the terminal potential difference, right?
yeah,
I'm thinking about this because now all of the 4 volts will not appear across the rest of the system. This is what will appear next. Wire XY has resistance 0.9 ohms and the potential difference across this much is 1.8 volts. It asks me then to find the current in the wire XY. So I guess this is pretty simple. I have the voltage across a known resistor. So I can just use this. So I would be V over R. So 1.8 over 0.9 will just be 2 amperes. And looking at this circuit, you can see this is a series circuit. So the 2 amperes that flows here will also flow throughout the rest of the circuit.
yeah.
The number of free electrons that pass a point in the battery in a time of 45 seconds. So remember how we defined current? How do we define current?
Current is voltage.
No, the
Um,
definition.
current.
Remember the order in which we studied these quantities. We studied current first of all. How did we define current? It's the rate of flow of charge,
Right.
right? If I can then find out the charge flowing, I also know that the charge will be a integer multiple of the fundamental charge, right? These are
Yeah,
the electrons which are going to flow. So for N, I can then just do IT over E. Does this make sense?
yeah,
So 45 times 2 divided by 1.60 into 10 to the negative 19. This turns out to be 5.6 into 10 to the 20. All right.
yeah.
Then it asks me for resistance R. So how do I find out this resistance? I already know the total resistance in this series circuit, right? I mean, I don't know it, but I can definitely work this out. So it would be 0.35 plus R plus this guy, right? And then I can just use V equals IR. So if I, for example, want to find the effective resistance first, I know this would be V over I, right? V was given as 4 volts and the current was 2, right? So
Yeah,
the net resistance is 2 ohms. And I know that since this is a series circuit, this would be the sum of all resistances. So 0.35 of the internal, 0.9 of the resistance wire, and R is what I can then find out. So 2 minus 1.25 is going to be 0.75 ohms. Okay.
yeah.
All right. Now your favorite question. A cell of EMF
I'm
1.2
falling
volts is
asleep.
connected to the circuit in B as shown in 5.2. Connection P is moved along the wire XY. Galvanometer reading is 0 when distance XP is 0.3 meters. So this distance, when this is 0.3 meters, this is the balance point, right? Calculate the total length of wire XY. How do we do this now? Hmm?
Like, I don't remember
When is balance achieved?
when the EMF of 1.2 is equal to the rest of the circuit.
When it's equal to what?
When our galvanometer reading is 0. So when it's 0.3,
I know it's
it's
0.
equal.
How would it be 0?
There's no deflection.
I know, but why would it be zero? That happens when
Because
the
there's enough
potential difference across
resistance.
here is equal to the EMF of this source, right?
Yeah,
Now you just found out that current. And remember how we were just talking about this equation, right?
yeah,
So 4 minus the 0.35 internal resistance times 2. So 4 minus, what is this? 0.7, right?
yeah,
So this is what? 3.3 volts. This is the potential difference which appears across this entire place. But then this length as a proportion of the entire length, this should be so that this equals 1.2, right? This length 0.3 must correspond to 1.2. So what entire length then corresponds to the full, what do you call it? Just a second, I've made a mistake here, sorry. Yes, this thing, which is that because if we look at this, then across this wire, what potential difference appears? So there's a drop across here and there's also the drop across R, right?
yeah,
So this would be 4 minus the current, which is 2. And then there's the 0.35 and then there's the 0.3. So this turns out to be what? No, what are we exactly doing wrong? No, what was R? Was R 0.3? No, sorry, R was 0.75, right? No, what I'm doing. R is 0.75. Right, so 0.75 plus 0.35 is 1.1. So there's 1.8 volts which appears across here, right? 1.8 volts appears here. But then I know that for the balance point, 1.2 must appear here. Yes.
yeah,
So then I can just use ratios that if this length L of 0.3 meters, if this corresponds to a voltage of 1.2, then what does the full length correspond to this voltage of 1.8? So then I can just cross multiply. So 1.8 times 0.30 over 1.2. This would turn out to be 0.45 meters. Does this make sense?
yeah,
Part 2. Fixed resistor is replaced by a different fixed resistor of resistance greater than R. State and explain the change, if any, that must be made to the position of P on wire XY so that the galvanometer reading is 0. So now this fixed resistor, this is replaced by a value which is larger than R. All right. Now let's think
yeah.
about this. So if this value is larger than R, what would happen to the what would happen to VT? If this is now a larger resistor, wouldn't it take up a greater share of the voltage? Yes, direct
Yeah,
proportion, voltage division. So now that leaves less for XY. So the voltage here decreases. Yes.
yeah.
Now what should be done? Now what should be done for the balance point to be achieved? How should the contact be moved? Should it be moved like this or like that?
To the right.
Good job, right? Because the voltage decreases. So then
Yeah,
you would want this length to increase so that the voltage increases again and it becomes equal to 1.2. I hope you do know why you said to the right.
yeah,
All right, good job. So you'll say potential difference across XY decreases. So contact must be moved to the right. For the balance point. Let's have a look at this one. Really quickly, we just studied this.
Another lepton is produced in the decay. The proton and then from a neutron and a fully positive. A lepton, is it the neutrino?
What is
Or
it
is
going to
it,
be, neutrino or anti-neutrino?
wait, um. Leptons, it's gonna be a neutrino.
Be more confident. Yes, this is the answer.
Okay,
State the name of the interaction that gives rise to this decay. So
State the
what's
name.
this force that gives rise to this decay? It's a weak nuclear force,
Weak nuclear, yeah, okay,
all right?
yeah.
State which of the three particles has the largest ratio of charge to mass.
It
Now
can't be a
charge,
neutron.
yes, charge to mass. So which has the largest charge and the smallest mass?
Is it gonna
So
be a B positive
if you
particle?
think about a proton has a charge of positive 1 e, right? And it
Yeah,
has a really large mass.
yeah,
Compare that with a beta positive particle, which also has a plus 1 e charge, but it has a much smaller mass. It's going to be beta plus. Yes.
yeah.
Use the quark model to show that the charge on the proton is plus e. We've done this a lot in class. What's the quark composition of a proton?
It was up, up, down.
Excellent. And what's an up quark? What's the charge of it? UCT was?
Yeah.
What's the
Sorry,
charge of an up quark?
of an up quark, 2/3
Yes,
positive.
so two up quarks, positive 2/3e. And what of the down quark?
Minus 1/3.
Which will give you plus
One.
e.
Yeah.
Good job. Part 5. Quark composition of the proton is changed during the decay. So this is what beta positive decay, right?
Yeah.
Now, what change must have occurred to the quark composition? Again, honest to God, I don't remember this. This is how I'll remember it now when the question is asked. I'll say that for the beta positive particle, this must have been 0, 1. So for the emission of this, the proton number must have reduced by 1. Yes.
Yes.
So this must be a neutron, and this must be the proton. Now, as you just said, a proton is UUD. What's a neutron? A proton is UUD. What's a neutron? You there?
Yeah, sorry.
If a proton is UUD, what's the neutron?
UDD.
So what changes happen in the quark composition?
Up to down.
Yes. Up to down. Pretty easy. How about, no, you can't do this one. Skip. 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 We're done. So how much time did it take us? Less than an hour.
Nice.
In all the explaining I was doing, less than an hour.
Yeah.
If I can do this in less than an hour with explanations, then you can do it in an hour without explaining, obviously. So we just did summer 21, paper 21. You have to do summer 21, paper 22. Let me message as well so that we remember. Summer 21, paper 22 is homework. This has to be done in any condition. after Eid because the next class will probably be on Saturday or Sunday, right? Then we'll do another paper in class and then I'll give you one more for homework. Do time yourself. All right. And be strict on yourself and give yourself only an hour to do this.
Okay,
Okay. Done. No problems.
yeah.
All right. Then